Let's take a look at how we can use this formula we saw yesterday. So, exponential function. From yesterday, what we saw was e to the iota theta plus 2ik pi would be the same as cos of theta plus 2 pi k plus I sine theta plus 2 pi k. But of course, the cosine and the sine, that 2 pi k that's repeating, it'd just be the same as cos theta plus I sine theta if k is some integer. But cos theta plus I sine theta is the same as e to the iota theta. So now what we're basically saying is, hang on, e to the iota theta is the same as e to the iota theta plus 2ik pi. They are the same thing. So this exponential is also a periodic function. Its period is not 2 pi though, 2 pi I, because it's repeating every 2 pi I. So how does that help us? All right. Let's go and prove some identities. Now, remember we saw these ones the other day, and they can be useful. The z to the power of n plus 1 on z to the power of n is equal to 2 cos n theta, and the subtraction one was 2i sine n theta. And that basically is because we're talking about complex numbers where the modulus is 1. And when that's the case, the reciprocal actually turns out to be the same as the conjugate. And so what we're really saying there is when we add a number with its conjugate, we get twice the real part. And when we subtract the conjugate from the number, we'll get 2i times the imaginary part. That's all that's really saying. If I rearrange those, I can get some formulas for cosine in terms of exponentials, but also sine in terms of exponentials. So we now have these ones. The cosine of n theta will be a half of, but now it's a number plus its conjugate in exponential form. And the sine of n theta is 1 over 2i, not 1 over 2, but 1 over 2i, the number minus its conjugate in exponential form. Let's now go and prove some stuff. How about this simple one we've seen so often now? Sine squared plus cos squared is equal to 1. Here's another way we could prove that. If I substitute in our new relationships for sine and cosine, I will get this result. I've got a common factor there of a quarter that I'll pull out. The I squared is going to be negative 1. And then when I expand out these quadratics, I'll get the following pieces. But we see some cancelling that happens in there, and I'm basically left with just a quarter times 4, which is 1. So sine squared plus cos squared is 1. Okay, what about this one? Sine cubed theta is 3/4 sine theta minus a quarter sine 3 theta. Well, sine cubed, I'll substitute in that relationship for sine. We're going to cube that. So the denominator becomes minus 8i, and on the top our cubic expansion. Now if I group these so that the conjugates are together, because then I can get the sine and the cosine back in, because that's all to do with the conjugates added together and conjugates subtracted. So with the 3, I'll get a number minus its conjugate, and the negative 1, I've also got a number minus its conjugate. And they're over 2i, so we know we've got the sine relationship there. So that's going to be 3 sine theta, and the other one will be minus sine 3 theta. And there's our proof. Quite a lot quicker than doing it the other way. How about this expansion? So the product to sum formula. 2 sine alpha cos beta. So we'll substitute in our new relationships there, and we'll do our multiplication. So the denominator becomes 2i. Let's group the conjugates together, and I've got a number minus its conjugate on both of those. So they're going to be sine. They're both over 2i, which is what we want. So I've got sine of alpha plus beta plus the sine of alpha minus beta. There's a nice little proof of that one. Finding roots of numbers now. Yet another way we could find the square root of a number. So let's find the square roots of 1 minus root 3i. Now we'll put it in exponential form. So 1 minus root 3i would become 2e to the power of minus I pi on 3. But what we just saw was, hang on, remember our new relationship. the power of minus I pi on 3 will be the same as minus I pi on 3 plus 2I pi k. Our exponential is a periodic function, so long as k is an integer. And that will allow us to generate solutions now. Because z squared, well, it's going to be the square root of 2 when I find z, and then I'll halve the power. I want two solutions because I'm looking for the square root, so two consecutive numbers, 0 and 1. And there's my two answers in exponential form. If I want the actual number, then we can go back, well, first we go mod arg, but then put it into Cartesian form. We've got our answer for the square roots. Let's look at some HSC ones. So 2020, what's the maximum value of this expression? Now you'll notice it was question 9, which means it actually was one of the multiple choice questions. So I won't show you what the options were, we'll just actually work out the answer for this. If I let z equal that complex number e to the iota theta, what I do know is the modulus of z is 1, because I can see that the coefficient of that exponential function is 1, so that must be the modulus. So all of the solutions for z lie on the unit circle. We want the solutions where modulus of z minus 2 plus the modulus of z plus 2. We want the biggest it could be. So what does that mean? Well, remember, modulus of z minus 2, we talk about what's the length of the vector that joins z to 2. So if I pick a point on this circle and join it to 2, we say, what's the length of that vector? And then modulus of z plus 2 would be joining the same point, but now let's join it to negative 2. And what we're asking is, when is that a maximum, the addition of those two lengths? Because as we move z, let's say I was to move from where I am now and move around in a clockwise way. And as I move clockwise, well, the vector on the left is going to get bigger, but the one on the right is going to get smaller. And so we say, well, what position will it be the biggest? And actually, it's where I am right now. So it'll be when it's plus or minus I. Okay. How do I know that? Well, if you keep going logically until you get to the x-axis, and you can then work out quite easily what that is and see that, well, hang on, that's going to be shorter than the one up the top here. So that one must be the maximum then, if it gets to the biggest point. All right, let's work it out then. What is the modulus of I minus 2? That's root 5. Now, because I've got a symmetric shape, that must also be the length of the other one, so I know the maximum is 2 root 5. Okay, 2021. This one was in question 14, so about halfway through the paper. By using part I or otherwise, well, part I, it was one of those ones where it asks us to prove a trig result. Okay, I'm not going to worry about doing that now. We'll just take that to be true. Cos 5 theta is 16 cos to the power of 5 theta minus 20 cos cubed theta plus 5 cos theta. So using that, or otherwise, you got another way of doing it, by all means, go and do it. Show that the real part of this complex number, e to the power of I pi on 10, is the square root of 5 plus the square root of 5 over 8. Well, we know what the real part is, because that's exponential form. The real part would be the cosine of the argument. So the cosine of pi on 10. So essentially this question is saying, show that the cosine of pi on 10 is that expression. They asked us to use part I or otherwise, so let's use it. We'll make theta pi on 10. Because we're trying to find cos pi on 10, our relationship has all these cos thetas in it. Yeah, it makes sense. Let's make those cos pi on 10. Now, using the relationship, all these three terms will add up to be cos 5 theta. Well, 5 times pi on 10 is pi on 2. And the cosine of pi on 2 is 0. If I now let x equal cos pi on 10, we get this equation. So cos pi on 10 is one of the solutions of this equation. We're getting closer. All we now got to do is solve this, and hopefully what we're looking to find is one of those solutions, and we match it up and go, yeah, righto, that is cos pi on 10. Well, the first thing I'm going to do is divide everything by x, which I can do, because x doesn't equal 0. We're saying x is cos pi on 10. That's the one we're looking for. So it's okay to divide by x. I'm not dividing by 0. And that's a quartic that looks like a quadratic. I can use the quadratic formula, and now we're getting there. Because x squared is 5 plus or minus the square root of 5 on 8, which matches what's inside the surd that we want. Well, that's x squared. I now know cos pi on 10 is potentially one of these two things. I know it's got to be the positive square root, because the one thing I do know about pi on 10 is it's acute. So the cosine is going to give me a positive answer. So it's not going to be the negative square root, it must be the positive square root. But the question now is it 5 plus root 5 or 5 minus root 5? Now, I know they told us to show it was 5, which one was it? Plus or minus? It was plus. They asked us to show that one. But we can't just go, oh, it's that one. We have to explain why is it the plus, not the minus. So at this stage, if I get a rough decimal approximation, and no, I can't just go to my calculator and go, what's cos pi on 10? Oh, it's that one. No, that's not showing it. But I do know it's either 0.59 or 0.95. It's one of those two. So I'm just going to draw the cosine graph and investigate. Okay, here's my cosine graph. I know that pi on 10 is on the left side of pi on 4. I picked cosine pi on 4 because that's one of our exact values, and I know that's about 0.71. And look at these two solutions. One is on the left hand side of 0.71, one is on the right hand side of 0.71. It would be tempting to pick then the negative because it's on the left hand side. But remember, we're looking for the y values, not the x values, because we want to know what the cos of that is. And if we look at the y values, actually the one on the left has a bigger y value than the pi on 4 answer. Therefore, cos pi on 10 must be the square root of 5 plus the square root of 5 on 8. But remember, that wasn't the actual question we were solving. It wasn't find cos pi on 10, it was the real part. So I should now conclude with the final statement. Well, I now know that the real part of this is the square root of 5 plus root 5 on 8. 2023. This also is in the middle of the paper, so question 14. Z this time is e to the power of I pi on 6, and W is e to the power of 3i pi on 4. They're giving us a lot of hints here. First write Z and W in Cartesian form, or otherwise, if you want to do it another way. Show that the modulus of Z plus W squared is 4 minus the square root of 6 plus the square root of 2 all over 2. Well, let's put them in Cartesian form. That's what they said. The first one, Z becomes root 3 on 2 plus a half I, and the W becomes minus 1 on root 2 plus 1 on root 2i. Now, I can now work out the modulus of Z plus W. So Z plus W, grouping the reals and imaginary together and finding the modulus of that squared, which would be the real part squared plus the imaginary part squared. And what do you know? We end up with 8 minus 2 root 6 plus 2 root 2 over 4. But there's a common factor of 2 in that. We get what they're looking for. That was the first part of the question. Now they bring vectors into the question. So the complex numbers ZW and Z plus W are represented by these vectors, OA, OB and OC. We now have to show that angle AOC is 7 pi on 24. Again, let's draw a diagram to get our head around what they're saying. So the first vector OA, I know the argument's pi on 6, so it's going in that direction. The second vector OB has an argument of 3 pi on 4, so it's going to the left, like that one. And the third vector would be the diagonal of that parallelogram when we draw it up. So there's C. We want to find angle AOC. What do we know? Well, I can work out angle AOB. I've just got to subtract those two arguments. I know that's 7 pi on 12. Hang on. 7 pi on 24, 7 pi on 12. That's giving me some ideas because one is half the other. What do I know about this shape? It's a rhombus. And I know diagonals in a rhombus bisect the vertex. So it's going to cut that angle in half. The angle AOC will be a half of AOB, which means it is 7 pi on 24. We've got our answer. Ah, well, now deduce this. The cos of 7 pi on 24, therefore, is the square root of 8 minus 2 root 6 plus 2 root 2 all over 4. I'm going to use the cosine rule on that triangle. And the three sides of the triangle are the modulus of z plus w, the modulus of z, and the modulus of w. The cos of angle AOC will become that expression. That's why they asked us to find the modulus of z plus w squared. Well, AOC, that's what we just worked out, was 7 pi on 24. Ooh, how did I tidy all that up? Remember, modulus of z and the modulus of w were both equal to 1. So on the top of the fraction I've got 1 minus 1, and on the bottom of the fraction I'm saying times 1. Now look at our fraction. Modulus of z plus w squared divided by the modulus of z plus w are half of the modulus of z plus w. It's half of what we worked out before. We have the answer. Now let's get to some good ones. Question 16s. So 2023, strap yourself in for this. Okay, complex number e to the power of 2i pi on 3. Show that 1 plus w squared is equal to 0. Hang on, some of these things are feeling very familiar. Where do we see 1 plus w squared equals 0? Are we talking roots of unity here? And if you look at what they gave us, indeed, that is one of the cube roots of unity. Can I just say that? Possibly not, but at least it gives me some ideas that I might be able to use in this question. Let's actually work out what 1 plus w squared is though. Substitute in. But hang on, argument of 4 pi on 3, remember, exponential periodic function. So it would be the same as e to the power of minus 2i pi on 3. Ooh, I've now got a number plus its conjugate. That means I've got twice the real part. Okay, I went the long way around to that. Now I look at it, I went the wrong way about it, because I could have just gone twice the real part. But yeah, look, that's what we're going to end up with, because you'll notice I've got, eventually, I've got a number that's conjugate there. Oh, I could have done that so much quicker. If you spotted that was a number plus its conjugate, you could have just gone straight to twice the real part. Anyway, we end up with 0. We have shown that 1 plus w squared is equal to 0. Mind you, notice this. See, when I went to exponential to mod arg, I kept the argument as minus 2 pi on 3. I didn't jump to it and say cos of 2 pi on 3 minus I sine 2 pi on 3, because that's not what the math says. That's effectively what we're using there. Right? To move from exponential to mod arg, we keep the argument the same. Then we might make a statement like, sine and cos odd and even functions, or we might say, these are conjugates, and then change the sign. We need to acknowledge that they're conjugates. We don't just jump straight to it. Oh, here we go. This is the good part of the question. The vertices of a triangle can be labelled A, B and C in either clockwise or anti-clockwise direction. Well, that's nothing new. That's just how we label triangles. They're always in cyclic order. Whether you go clockwise or anti-clockwise doesn't matter. Three complex numbers, A, B and C, are represented by these points. Okay. Now, depending on which way round we went, as to which point would be which complex number. Show that if we went in the anti-clockwise direction, so the left-hand triangle, then A plus BW plus CW squared will equal 0. So it's the left-hand triangle we're talking about. There's the left-hand triangle. Okay, so what do I know? I'm going to translate that vector AB up so it's joining C. Now, why did I do that? Okay. I know the vectors are equal in length because it was an equilateral triangle. So this vector up here is also the same length. I now know that angle in there is 2 pi on 3 because the arguments of the vectors and so on. So what that now is telling me that the vector AB, which is the same as this one here, would be the same as getting the vector CA and rotating it 2 pi on 3. Well, cis 2 pi on 3 was W. That's what W was defined as. The vector AB is head minus tail. So B minus A is equal to W times A minus C. Now I want to play with that. So if I expand out, but hang on, I've done more than just expand out there, haven't I? I've also multiplied both sides by w as well. Now why did I do that? Because I notice in what I'm trying to prove, I've got w squared and w. What I've got is just got w. So I thought, oh, well, multiply both sides by w. That'll bring out some w squareds and some w's, and maybe I can play with that. Okay, let's group the a and the b and the c, and hopefully the coefficients are going to turn out into what we want. W squared's coefficient is c. Good. W's coefficient is b. Good. Oh. The coefficient of a is not 1, it's minus w squared. But we know 1 plus w squared is equal to 0, so in fact that is equal to 1. We've got the relationship. Question 16, eh? It keeps going. Alright, it can be shown that if we went the other way, so if we went clockwise instead, then the relationship would become this. And they point out, don't go and prove that, okay? They're telling you, that's the other case, you can just use that. Don't go and prove it. Right? But that would be if we took the other triangle, what would happen? So now, if it is an equilateral triangle, a squared plus b squared plus c squared must equal ab plus bc plus ca. Well, at least that's what they're telling us. We got to show that. These are the two things we now know. One, we worked out. One, they told us. But we know those two things. So if the triangle is equilateral, we know one of those must be true, depending on whether we went clockwise or whether we went anti-clockwise. But one of them is definitely true. So if I multiply them together, I must get 0, because one of those things will be 0. Doesn't matter what the other one is. Multiply by 0, we get 0. Okay, let's see if I can now turn this expression into the one we're looking for. Whew, expand it out. There it is. Okay, I'm going to group everything that has a squared, b squareds and c squareds on the left hand side, because that's what I'm trying to show. Everything that has a b's and b c's and c a's on the right hand side. Let's see if we can get these coefficients correct. Well, a squared's okay. That's about it at this stage. But remember, we're playing with roots of unity. We know two things. We know w cubed is equal to 1, and we know 1 plus w squared is equal to 0. Using those two things, we should be able to do it. Okay, I'm going to tidy that one up straight away. Because look, on the left-hand side, w cubed, well, that's 1. W cubed, that's 1. Look on the right-hand side, I've got a common factor of w squared plus w. Hang on, w squared plus w to the 4, w cubed is 1. That's also w. So all of that I've done just using the fact w cubed is 1. Okay, we're close. I now want the coefficient of this to be 1. At this stage it's minus w squared plus w. That's where I'm going to use the other fact. Because w squared plus w, well, 1 plus w squared is equal to 0. So that is negative 1. Negative times negative is a positive. We have the result. 24, part B. So this time, they've actually told us it's a cube root of unity, this one. So we're working with one of the cube roots of unity. But now we've got this other number, gamma. And it's a cube root of w. We have to show that gamma plus the conjugate of gamma is a real solution or a real root to this cubic equation. Well, if gamma cubed is equal to w, what I do know is gamma is also going to be a root of unity. But it'll be a 9th root of unity, because it's a cube root of a cube root. So it's a 9th root of unity. It's one of them. I don't know which one, but it'll be one of them. Show that. Let's substitute into our equation. We want to show that this ends up being 0. So when I expand out my cubic, I get this on the right hand side. Okay. I know gamma is a complex 9th root of unity. Well, as like all complex numbers really, not just roots of unity, gamma times gamma conjugate will be the magnitude squared. We're talking about a root of unity. That'll be 1. Anytime I see in this gamma times gamma conjugate, I can change it to be 1. So on the first one here, or not the first one, the second term, I've got gamma squared times gamma conjugate. So there's a gamma times a gamma conjugate in there. That's equal to 1. I'm left with gamma. The next one, I'm left with gamma conjugate. And then gamma cubed we said was W, didn't we? It was a cube root of, so that's now become W. And then, right, okay. So we've simplified it down a little bit. But there's some cancelling in there. I'm now left with W plus the conjugate of W plus 1. But we have some information about that. Oh, I did it the sensible way this time. Twice the real part. So it's twice the real part. So it'll be 2 times the cos of 2 pi on 3. We get 0. There's the solution. The other thing I really need to point out, because remember they didn't just say it was a root, they said it was a real root. Maybe it was over the top, but I said, well look, I know it has to be a real root because gamma plus gamma conjugate is twice the real part. So it must be a real number. So it is a real root. Part 2. By using part I, find the exact value of cos 2 pi on 9, cos 4 pi on 9, cos 8 pi on 9. And then from that, deduce the values, and they put S in parentheses to highlight maybe there's one answer, maybe there's more than one answer. That's for all integers. And you've got to justify your answer. You've got to just write an answer down. You've got to justify why you had that answer. Okay, well let's do the first part. Gamma cubed was equal to W. Our exponential is a periodic function, so I can add on 2 pi I k. I want 3 consecutive solutions. I've gone with -1, 0 and 1. Okay. Can divide by 3 and I'll get that gamma is e to the power of 2 I pi on 9 plus 2 pi I k on 3. There's my 3 solutions for gamma. They are indeed 9th roots of unity. Obviously it's not all 9 of them. There's 3 of the 9th roots of unity sitting there. Well, gamma plus gamma conjugate then would become twice the real part on all those. So 2 cos minus 4 pi on 9, 2 cos 2 pi on 9, 2 cos 8 pi on 9. Well, looking at what we want, I don't want -4 pi on 9, but cos is an even function, so I can change that to be 2 cos 4 pi on 9, and I've got the 3 things that they want. Excellent. So gamma plus gamma conjugate are those 3 possibilities. But they were the solutions, remember, of that equation, z cubed minus 3z plus 1. They are the 3 roots of that equation. So the product of those roots will be -1. So we get our value, it's -1/8. Okay, but now how do we deduce the next bit? Remember, gamma was equal to that expression, and what we said, we chose -1, 0 and 1. But it could have been any 3 consecutive integers. So I could have said 1, 2, 3. I could have said 2, 3, 4, although I've written it in a strange way. I could have said 3, 4, 5. I could have said 4, 5, 6. The reason I've written it like that, what I'm essentially saying is, every time I swap one out, I replace it with 3 more than it. So when I had 1, 2, 3, if I wanted to go to the next one, it would be 2, 3, 4. The 1 was replaced with 4. 3 bigger. And then when I swapped out the 2 for the 5, again, 3 difference. So I'm saying k is always replaced by k plus 3. This expression is now replaced by the second expression I've written there. Well, what is the second expression? I can now play around with the second expression and look what I get. It's the same plus 2 pi I, periodic function. I don't need the 2 pi I. So it's going to be the same as e to the 2 pi I, 1 plus 3k. Hang on, it's the same. The value doesn't change. So if the value doesn't change, every time I swap one out for a new one, and the value doesn't change, well then that product's not going to change either. That product will always be -1/8. It will never be anything different. There we go, we got through it. So 3e.